Okay, so good evening, everyone. Welcome to the penultimate talk of the 2021 edition of the STEMS qualifier camp. So we hope all of you have been having a great time here and will continue to do so in the last two talks as well. So now we have Alok Laddha, who is a faculty at the Chennai Mathematical Institute. So he's in the physics department. So he completed his bachelor's at the University of Bombay and his PhD from the Institute of Mathematical Sciences in Chennai. So today he'll be giving us a very nice introduction to the beautiful world of quantum physics. So his talk is aptly titled Quantum Theory from Gold to Gluons. So I really hope all of you enjoy, and over to you, Professor Alok, without any further ado.
Okay, thanks Anirudh and Amik especially for organizing this so many talks. So I don't know, I should make a disclaimer that the excellent introduction, I'm not sure obviously, but I will try my best. But one thing I want to say is please feel free to interact me anytime. I mean, don't just ask me questions. I mean, the talk is designed in a way that if you ask questions, it will be better. So let me start. I slightly changed the title. So quantum theory, basically gold standard of physical theories. So what I want to do is basically give you kind of an overview of what has happened in the last 100 or so years in the world of quantum physics. So let me basically start with some brief motivation. So our understanding of the world around us was, for 300 or so years from time of Newton to early 20th century was kind of essentially the same. And it was premised on idea of classical physics. But there were two major scientific developments, which are often called almost revolutions in scientific world. One is theory of relativity, which I'm sure a lot of you have heard about, and one is quantum mechanics. And this basically happened in the 1910s and 1920s, the early part of last century. And then the 5 decades that followed, physicists realized that actually these two principles, although they are very different theories to begin with. This theory of relativity is essentially a theory of high-speed classical objects, and theory of quantum mechanics is theory of atoms and electrons and so on and so forth. But actually they were in fact unified into a framework, which was then called quantum field theory. And this single framework actually explains most of the phenomena we observe in our world today, from physics inside the nucleus to physics of very exotic objects in galaxies, like say neutron stars. So basically what I want to do is give you sort of as Anirudh said, overview of some of the evolution of quantum theory and how it has helped us understand and also shape the world around us. Yeah. So of course we don't have time to learn quantum mechanics, but one nice way to understand quantum mechanics, you have some fun with it in 1 hour. So we can try to answer questions which are fun questions. So one obvious question that is interesting for everyone is, why is gold yellow? I mean, this is a question that if you just, it's a question that should everyone should find puzzling. And the reason is that most of the metals we see around us are gray. I mean, they're kind of, they don't have any color. And so this is a question. And if we can see that if quantum mechanics can answer this question, then okay, we get excited by quantum mechanics and we can try to study it further. Now, so the reason most metals are gray is because they don't really like to absorb any visible wavelength of light. So roughly visible wavelength of light, I mean roughly between 400 and 800 nanocentimeters. So if you have wavelength which is larger than 800 nanocentimeters, then these are called infrared light in infrared region. And if the wavelength is smaller than 400, then it's called ultraviolet light. And most of the metals we see, they do not like to absorb light in this range, which is the visible wavelength that we can actually see. So what that means is that they basically reflect all the visible light. So because they reflect all the light gets mixed up, different colors get mixed up, and eventually they appear colorless or gray. So but okay, we can still, I mean, the first thing to ask is why is it reflecting? Why some metals reflect all the light and why some metals like gold do not reflect some and reflect the other light? So we have to go to something we learn in school first. So we learn that, I mean, this is something I hope that most of you would have at least seen in school, that electrons in an atom move in certain discrete orbits, which are labeled by, some vague letters like S and P. They're called S orbitals, P orbitals, etc. They're like planets around sun, basically. I mean, that's the model of atom that we have. That model in some sense still holds true. So if you shine light on a metal, what happens is that the electrons, which are the outermost electron, which is furthest away from the nucleus, so they absorb the light. And if the energy of the light is sufficient, then the electron can jump from one orbit to another orbit. And so that means they have eaten up the light and they got excited. So if they ate up some wavelength of light, then that wavelength will not be seen. And so because of that, the light that is coming out reflected, it will appear to have some color. So for most metals, it turns out that this requires light with wavelength less than 400 nanometers, which is called UV light. So essentially, gold is doing something different, and this is what we want to understand. So that's one fun example of why power of quantum mechanics. So please ask me any question at any point. Okay. So first of all, gold is anyway a little bit special. Even if you don't like physics and you like chemistry, then also you'll be a little bit fascinated with gold, because it's one of those rare naturally occurring metals with unusually high atomic number. So its atomic number is 79. So it has 79 protons basically. So compared to nucleus of hydrogen, which has 1 proton, this is like a monster. It has a large number of protons. But okay, there are other elements also which have large atomic numbers. So what is so special about gold? That it became yellow and people fought so many wars over it. So we want to understand, like, where do these colors really come from? So we have to delve deeper into quantum mechanics than what we learn in school books about these orbits of electrons, etc. So the first thing we have to understand about quantum mechanics is the first model of atom that Niels Bohr proposed. So in Bohr's model, this is a model that he proposed, and it turned out that it really explained hydrogen atom and its properties very, very well, is that electrons moved around the nucleus in discrete orbits, like planets around the sun. And this was the Bohr's explanation of what an atom would do, or an electron in an atom would do, if you shine light on it. So when you shine light on a matter, one of the two things can happen. If the frequency of the light, which let's just call it this Greek letter nu, which physicists like a lot, is such that the energy of light, which is h bar times nu. H bar is a universal constant. It doesn't change if you are living in Earth, or it's a number which is same in the entire universe. So even some aliens, if they knew about h bar, they would have the same h bar. So h bar nu is basically the energy of light. And so if the energy of this light that you shine on a metal, if it's equal to the gap between two outermost orbits, then this light will get absorbed, otherwise it will be reflected. So this is how you could explain what light will do to an atom, according to Bohr. Now, for most metals, as we discussed earlier, in the visible spectrum, whatever light, the gap between these orbits is not such that it's too large. So the light in the visible spectrum is get reflected. I mean, the electron doesn't get excited from one orbit to another. It's like, you are on first floor and you need some energy to go to the second floor. But if someone just gave you, a couple of biscuits and you didn't have energy, then you won't be able to go and sit on the first floor. So that's what happens. So that's why they appear, most metals appear.
Excuse me?
Yes.
Yeah, can it jump multiple orbits at the same time, or just like one?
Well, that depends. Yeah, exactly. That's a very good question. So the idea is that as we will see that this question itself, we have to see it a little bit in more detail, in the sense that what does it mean for electron to jump orbit one to the other? So we'll come back to your question once we look at the jumping of electron in a little more detail. But
okay.
Yeah. So it turns out that, so basically this was Bohr's picture of the atom, basic atom, like hydrogen atom. So if you take this picture seriously, then the only way that gold will appear anything other than gray is if, in addition to UV light, suppose it absorbs blue light. So if it absorbs blue light, remember, is the part of the visible light which is the which is the least wavelength in the visible side of the spectrum. So if blue is absorbed, then every other light will be reflected. An average of every other color is yellow, and that is why gold will appear yellow. So actually, the color of gold really has something to do with blue rather than yellow. So the idea is that we need to understand why gold absorbs blue light and reflects all the other lights. So that's the puzzle, and we want to understand if Bohr's model can explain this puzzle. But it turns out that okay, let me just. Okay, so let's look at gold's. Let's apply Bohr's idea to gold atom more seriously. So now electrons. So this is Bohr's model, of course, that electrons are orbiting around nucleus, are like planets around the sun, and they move only in like discrete orbits. But the more the number of protons are, the charge of the nucleus, of course, as you can see, is more, because each proton is positively charged. And so then the force on the electrons is more and more as you start increasing number of protons inside a nucleus. So the force on an electron in a gold atom is much more than the force of the nucleus in a hydrogen atom. So the electrons will move faster and faster. But if the velocities become too high, then Einstein's theory of special relativity comes into picture. And I think, so I want to say something which you may have at least heard or read in some popular magazines, that if you accelerate particles to very high speed, then their mass increases. I mean, so, this is one of the immediate corollaries of special theory of relativity. So, okay, so it is a possibility that this could happen in gold, that, because the nucleus is very, very heavy. So it may happen that electrons move very, very fast, and maybe something unusual happens because of that, and gold acquires color. But okay, so in itself, it doesn't explain. And it turns out that this model of Bohr was actually not the most accurate model. And this was explained by de Broglie, who said that, well, Bohr assumed that the electrons are still particles. They move in discrete orbits, but they're still particles. And as people understood quantum mechanics a bit more, I mean, especially de Broglie, he said that, really what the electron is not really a particle, but it's really like a wave. And so it's this wave which is, as shown in this picture, it's this wave which is kind of circling around the nucleus, and it's kind of the average position of the wave is like what we think is the electron, but there is no electron. There is basically like a wave which is like orbiting around the nucleus. So this was a slight improvement on Bohr's model, which in some sense we could say it became more quantum than earlier. So let's see if this helps us in understanding why gold is yellow. Okay, so there is some improvement, because as the electrons get faster and heavier, so their mass increases, then you can immediately check that if mass of an electron increases, then its wavelength is actually inversely proportional to its mass. So if its mass increases, and mass is same as energy in special theory of relativity, so if its energy increases, then its wavelength decreases, then the radius of this orbit will decrease, because you want to pack more waves. If the wavelength decrease means you want to pack more waves inside an orbit, in one orbit. So obviously the radius has to go smaller, if the wavelength went down. So the radius of the orbits will decrease. So if this happened, if the following thing happened, that the outermost orbit shrunk, but the inner orbits didn't shrink, then the gap between the two orbits will shrink. If the gap shrink, then the energy for the electron to move from one orbit to the other will be lesser, and it is possible that it could start absorbing visible light of smaller energy. But of course, you could immediately see that there is a catch. I mean, this couldn't possibly make sense, because the outermost electrons actually feel the least force because they are farthest away from the nucleus. So we expect that actually these orbits will be shrinking much lesser than in fact innermost orbits. So if we use this logic, then it looks like the gap between orbits will be even more than what it was in the classical theory. So it looks like quantum mechanics, rather than explaining, does something opposite. It's somehow trying to say that gold should appear more gray than other metals, which is not true. But it turns out that this de Broglie proposal is also not quite accurate, and so we have to go more quantum now than what we have so far. So, is there any question so far?
You just said if electrons are waves, how will it feel force? It's not a particle.
That's an excellent question. So the point is that in quantum mechanics, I mean, unfortunately, we don't have time to go full into quantum mechanics, but there is a wave-particle duality in quantum mechanics. So, it is, you could think, for your question, you could think that it is both. It is, it is a wave. That wave is feeling a force, but if you want to visualize that force, then you could also think of this wave as manifesting as a particle, as a particle. But if you look at equations of quantum mechanics, then you see that even waves feel force, and so it's not it's not unusual. I mean, for example, if you just create a wave with a string and then you can just disturb it, right? It will feel the force. So in that same sense, I mean, you can create a wave and then with a string and you kick it, then it will get.
It does mass like matter waves.
Well, yeah. I mean, that's a very good picture to have. That it's like, think of it like a matter waves, and so it will feel force.
All right. Thank you.
Thanks. Yeah. Thanks. So now we have to go more quantum. So because if we take this so far, whatever we are learning, it looks like we'll get opposite answer. So let's see what happens. Sorry, I'm having trouble switching slides. Okay, so let me give you like a 1-minute introduction. So now we really have to do some quantum mechanics. We can't just work with Bohr and de Broglie's pictures. So one thing is that quantum really means discrete. So I mean this is one line summary of quantum mechanics, because quantum also, the meaning of quantum is discrete. So basic tenet of quantum mechanics is that energy is not continuous, but it is made up of discrete quanta. Now, classical mechanics is premised on a very simple empirical fact. I mean, something we see in everyday world, that particles have definite trajectories under influence of external forces. So we can roll a ball on a slope and we know where it moves. In quantum mechanics, and this is why quantum mechanics was kind of called a revolution in physics, because the entire picture changed. The idea is that we can't really locate a particle. The most we can know about a particle is via this wave that de Broglie pictured. And I mean this wave, I mean in when we actually write equations, it's really called a wave function, simply because it's a function of space and time. So if x is like a space variable and t is time, so the wave that describes this electron is like a function of x and time. And this is, quantum mechanics is hypothesized on the fact that this is the most we can know about the electron. We cannot know anything more. Like classical particle, we can know position, velocity. No, quantum mechanics will say no. Only thing we can know is what this wave is or what this wave function is. And this wave function, we can ask, but what is this wave? I mean, what is physically this wave function? It's a little bit of a weird object. I mean, the easiest physical explanation it has is that if you square it, if you just think of it as a function and you square it, then it tells you what is the probability of locating the particle at a certain position. So if you square this psi xt, then it will tell you what is the probability that the electron is at a position x at time t. And there is an obviously there is a internal paradox here, that is there actually a particle or not? So physics is littered with unfortunate souls of people who have gone mad thinking about whether there is a particle or a wave or a both or what really happens. But for our purpose of the talk, and really in quantum mechanics, the most you can know about a particle is its wave function, and nothing more. You can't get more information than what is there in the wave function. So if nothing, you should get this out of this talk, at least, that it's a very different theory than classical theory. So in full-fledged quantum mechanics now, electrons around the nucleus.
Excuse me?
Yes.
Are we assuming like a universal clock in the T, or?
Oh, that's an excellent question. So right now, that we will touch upon this. So right now, yes, we are assuming there's a universal clock, in the sense that, okay, there is some inertial observer, and that is measuring the time. You are right that when we solve equation, we have to be careful with these things. But for the purpose of solving the gold color mystery, it's okay to just assume there's a clock. There's one observer with a clock.
I was wondering because you said that electrons could have relativistic speed.
Exactly. That's exactly, I understand. So that subtlety is very important when you actually solve the equation. But let's assume that there is some observer for whose time t that we are using now.
Okay.
Is that good? Yeah, thanks. Okay. So in full-fledged quantum mechanics, electrons around the nucleus are described by wave functions. And so now let's see if these wave functions can kind of help us understand the mystery of gold's color. Now, I've shown some examples of some wave functions of electron around an atom. So these wave functions come in different shapes. So if you can plot them, like the red guy, the first red guy is what is called an S wave. S wave because it's spherically symmetric, and it's like a so basically, if your electron is in this S wave, means that the probability of, so this red thing is describing the function psi xt. So we have frozen time here. So let's say time is like t equal to 0, and so this is a function of space x, and it's this shape is the shape of the function psi of x at a given time t. And similarly then, but that's not the only one. Electron can also have wave functions which look like the like this red and blue thingy, which is called a p wave. It can even have more complicated wave functions, which are called d waves, etc. So these are something that you sort of hear about in chemistry textbooks, s orbital, d orbital, but they really come from quantum mechanics. And these are like, you can plot them because they're functions, and this is their actual shape inside atoms. So now let's see if this helps us in understanding color of gold. Yeah, okay. So this is what I said earlier, that, okay, so, the waves, there is a symmetry in the problem, right? Because it's like, the potential is like electrostatic potential. So, there is the potential only depends on the radial distance. It's insensitive to angle, because of which your wave functions cannot look like squares or cylinders or something. They can only have this kind of spherical and close to sphere type shapes, which is what is shown in this picture. So S waves are, as we discussed, they are spherical. And it turns out that if you take this wave function for the S wave and you compute probability by squaring it, all of them have maximum probability close to the nucleus. So in gold, so this is interesting, because that means that you may have thought that the outermost electron in the gold atom is actually going to feel the least force. But if the outermost electron is in the S wave, then it's going to feel a lot, then that S orbit is going to shrink, because actually effectively the electron is very close to the nucleus. So the intuition we got from de Broglie was actually incorrect. If you look at quantum mechanics very closely, it turns out that even the outermost electrons, if they're in S orbit, these S orbits really shrink because of the special relativistic effects. But it turns out that if you compute the probability for finding electron in the P wave or the D wave, which are these elongated, oblique shapes, then the probability of finding electron is maximum, like the maximum is away from the nucleus. So these waves do not shrink as much. It's like electron is far from the nucleus, so it doesn't feel that much of the relativistic effect. D waves in fact stretch out, and the reason they stretch out is because S wave electrons like shrink, so they go close to the nucleus, so they shield the charge of the nucleus. So nucleus becomes kind of less positive charged for the D wave electrons. It sees less of the positive charge on the nucleus because it's shielded by the S wave electrons. So in fact, opposite happens for the D wave. It actually gets elongated. It goes farther out from the nucleus. Now it turns out that this is interesting. Because of this, what has happened is that blue light, it turns out that blue light can excite an electron from 4s to 5d. So 4s, the s orbit shrinks, the d orbit gets slightly elongated, and the gap between them becomes such that blue light can be absorbed by the gold atom and the electron gets excited. So, but it turns out that this gap is such that only blue light gets, roughly speaking, only blue light gets absorbed. Every other light is reflected, and average of all the other lights is yellow. So because of this, gold becomes yellow. And it's really, as we discussed, it's not so much yellow, but it's actually not blue. And that's the important upshot. So really, it's really, you would need quantum mechanics and relativity to explain the color of gold. Otherwise, you would not be able to explain it. So before I move on, is there any other question?
Yeah, I have a doubt. So 4s to 5d will be a specific discrete
I can't
wavelength.
hear Anish.
Hello?
Can anyone else hear him?
We can hear him.
Yeah, I can hear you.
Hello?
I think I can hear him. Professor, can you hear us?
Yeah, now I can hear. Yeah, sorry. Yeah.
Yeah, Anish, yeah, now you can continue.
Yeah, so 4s to 5d will be a specific wavelength, discrete wavelength.
Exactly.
But how will a discrete wavelength really matter when it's actually emitting a, like, how will it actually change the color?
Yeah. So what is happening is that you shine visible light. Now, if you look at the blue wavelength, let's say blue wavelength for simplicity is 450 nanometers. So it turns out that the energy, so you can now compute energy for these 450 nanometers. And that energy gap is precisely the gap between 4s and 5d now. So it absorbs only that one. And all the other colors, it reflects because the gap is not.
No. My question was, when we put visible light, we also put wavelengths of 451, 452.
Yeah, exactly. Very good. Exactly. So the point is that it will, of course, as when I'm saying 450, I mean, it will absorb in and around 450. But if you take 600 nanometers, it's not going to absorb it. It's going to reflect it. So what happens is going to reflect everything else roughly except the blue thing. And average of everything else is yellow. Because yellow is bang in the middle of all the other colors. So because of that, it appears yellow. So the thing is, it's not that it's yellow. It's not blue. That's the right way to look at gold. Maybe if people thought like that, they wouldn't fight wars over. Maybe people, if they knew quantum mechanics, they would be not so fascinated by gold. So okay, so that's the. I hope this kind of at least was a little interesting and told you how special relativity and quantum mechanics can explain some very unusual things that we see around us. So if there's no other question, I can go to the next part.
I had a follow-up question to Anish.
Yeah.
Yes, so 450 is a blue, one blue, and so as I said, 451 would be also blue, right? Like
exactly,
different blue.
Exactly.
So if we just, if you can just absorb only one specific wavelength, then it is just absorbing one out of many blues.
Well, yeah. It's not, these wave functions are spread out, remember. They are not like precisely at some position. So it will absorb energy, which is say between 440 and 460. So, basically the point is that it will maximum absorb the blue guys. So that, if you take a entire visible spectrum and remove shades of blue, then the color will start changing towards yellow. You see what I'm saying? What we call.
But I thought it was a discrete jump, like not a spread out one. Like it has to absorb only a particular wavelength, not a bunch of them, I thought.
Yeah, I agree. So what I'm saying is that if you look at, what I mean by that is that if you look at when we say 450 nanometers, it's like suppose the gap between 540 and 5s was say 452.5 or something. I mean, that was the jump. So it will absorb, like that wavelength energy. But of course, you see there is 45s, but there are also other orbits. So electron can be in 5s, but it can be 6s and 5d, etc. So it could be that but the point is that the maximum probability that it is absorbing is around the blue, in and around the blue.
Okay.
So because of that, I mean, yeah, the actual computation is a little bit complicated because it's not like it is absorbing, precisely the blue color somewhere and then you get exactly yellow or something. Right? But the dominant absorption is in one part of the spectrum, because of which the remaining colors look average out to give you yellow. Is that what you're asking? Maybe.
Yes.
Okay. Any other questions?
Sir, so for a particular gold atom, there are multiple wavelengths of light which are being absorbed, and they are overall of shade of blue.
No. Wait, I lost my screen. 1 second. Sorry about that. Oops. Yeah. So okay. So let's say that let's look at 4s orbital. So 4s orbital. Suppose this 4s orbital shrunk to some somewhere close to nucleus. So the probability of finding the particle in the 4s orbital is, let's say, at some radius r0 from the nucleus, maximum probability. So remember, the point is that when we say that the jump is discrete between these orbits, these wave functions are giving us probabilities. So when we say that 4s is the particle is closest to nucleus, it's like the maximum probabilities. But 4s itself is spread out. The particle is spread out. It's not sitting at one location. You see what I mean? So let me explain again. So 4s is a wave function which gives us a probability. It is telling us that the maximum probability for finding the particle is closer to nucleus. But it doesn't mean probability of finding the electron somewhere else is 0. So you see what I'm saying?
Yes, sir. So with respect to the actual position of the electron at that.
So let's say that the 4s. So let's say the probability of finding the particle around r0. So between say r0 and r1 is maximum. I mean, probability of finding the electron at r0 is maximum. So it's very large between r0 and r1. So you have the probability of finding the particle electron between r0 r1 is large compared to other radii, and you have the phi d where the probability of finding the electron between say r2 and r3 is large. So then the basically you see that you have to average over. I don't know if that makes sense. So it's not like you have electron at r0 precisely and r1 precisely, right? It's not. Is that making sense?
Yes, sir. Yes,
that's
sir.
That's why you get an average over blue. You see what I'm saying?
Yes, sir. Yes, sir.
But you think that the electron can be at r0. It can be at r0 plus delta being some small number, r0 plus 2 delta. But let's say it is probability of finding it at r0 plus 10 delta is very small. Similarly, let's say that in the phi d, electron being at r1 is maximum, r1 plus delta is slightly small, r1 plus 2 delta is slightly small, and r1 plus 10 delta is very small. So basically, you have to now look at all the wavelengths which can go from r0 to r1 or r0 to r1 plus delta. They are all okay. They will all be allowed. So that's why you'll get like not a discrete blue, but like an averaged blue. You see what I don't know if that made sense.
Yes, sir. Yes, sir. Understood.
Okay, thanks. Okay, any other question?
Sir, I have only another question. That is, the elements neighboring to gold in the periodic table, for those elements, this transition is not possible. Why?
That's interesting. I mean, they have other properties because of this, which unfortunately we can't go into. Like, for example, mercury. Mercury, because of the heavy atomic number of mercury, it has as you know, mercury is very different object than gold. It's like a liquid basically. So and it has a very shiny gray color. I mean, it's not like a dull gray color. If you take, for example, copper, it is red. So I mean, the similar kind of mechanisms that we are talking about, basically the combination of special theory and quantum mechanics affect all the heavy atoms in different way. For gold, special thing that happens is that its color becomes yellow, and that's the. But for copper, it will become red, for example.
Do we know quantitative results regarding this phenomena, or are they just qualitative?
No, they are quantitative, quite quantitative. Yeah.
I had a question.
Yes.
Does the energy requirement to jump from one orbital to another
yes
change on the position of the particle?
Well,
Because
so I think the important thing is there is no real particle, right? I mean, so
but I mean, we are assuming that there, I mean, somehow is a probability. Just when we do, I mean, it's
Yes.
a bit weird because we don't know, but we assume the probability to be the particle of some sort. Like it's a bit-
Exactly. So probability is telling you that probability is telling you. So
I
probability.
mean, it's still a probability of finding something there, right?
Exactly. So the point is that if your probability is say 99, say between probability of finding particle, let's say R naught is say maximum, say 40% or say 60% or something, and then say probability of finding particle close to R naught. Basically, let's say that probability of finding the particle between say R1 plus epsilon and R1 plus 2 epsilon is say 99%. So that is so for all practical purpose, you can think the particle is here between R1 and R1 plus 2 epsilon. Does it make sense what I'm saying?
Yeah. So what I was looking at is that the orbital shapes are not like symmetric on every axis.
No. Only S orbit is symmetric.
Yeah.
None of the other ones are.
Yeah. So does the energy gap change?
Between?
Depending on the position. I mean, okay, position is again a very vague thing. So suppose we assume, say, a range of positions, like a space.
So each of this. No. Each of the wave function, for each of the wave function, the electron, the particle, the would-be particle, whatever it is describing, is in a given energy state. It's in a given energy state. So
okay.
So the point is that we, of course, this requires us to understand quantum mechanics. The idea is that if the particle is in the S wave, the reason we think of this S D wave special is because they tell you that electron, if it is in S wave, it means that it has a definite energy. We can measure its energy. Although its location is uncertain, its energy is definite. So these are very special kind of wave functions in which energy of the particle, we can certainly say it is like, whatever, some joules or something. You see what I'm saying?
Yeah.
So you could have asked like why we are looking at S wave, P wave, D wave. No, why not something else? The reason is that these are very specific wave functions in which electrons are in definite energy state.
Yeah. Okay.
Yeah. Thanks. Okay.
Excuse me, sir. So we can think of these orbitals as a wave density of the electron, as in.
Sorry, I lost you, Ranjan. What did you say?
As in wave density of the electron.
It's yeah. You could think of it like that. It's like a probability density. You are right. Yeah, exactly.
So the as he said, the shape would matter, as in, for example, the dz square orbital. So there's a ring on that. So on the ring thing, if the density is there and near the center of the orbital, wouldn't there be difference in the?
No. So that's the point. So remember that when we talk about the wave function, this is all we know about the electron. So let's first start with that, premise. Now the point is that if you say that the electron is in S wave, which means that it's described by this S wave function, one thing we can say for sure is that it has a fixed energy. I know it sounds very counterintuitive because if the particle is not in a given position, how can it have definite energy? But this is like a little bit of a magic of quantum that, that
all points in the orbital.
Sorry?
At all points on the orbit, in the orbital.
That is not that we cannot ask that. So the point is that we cannot. Okay. Yeah. The point is that we cannot talk in that terms at all. All we can say is that the electron is described by the wave function and it has definite energy.
Okay.
Right. We cannot ask that, does it mean that electron at some point has one energy and the other? No, that's not like that. It doesn't work like that. The wave function has a you can assign. So in classical mechanics, we assign energy to a given configuration of the particle, right? If you give me like a position and momentum, then we know what its energy is, right? Of the particle in classical mechanics. So here, think the same language, but instead of looking at the trajectory, think of the wave function. So you give me a wave function, then I can tell you whether that wave function has a definite energy or not. And these S and P and D orbitals, that's why they're special wave functions, because these are wave functions in which electron has definite energy. So it is not, that does not mean the electron is a particle at one point has some energy or other. That question we cannot ask because there is no electron, there's only wave function.
Sir,
Okay, so there is
uh,
not much correlation between radius of the orbital
No,
and the
there's
potential
of course there
energy
is
of it.
of course there's correlation. Of course there is correlation when we solve equation. But the important thing is we assign energy to wave function. Just like in classical mechanics, we assign energy to the trajectory. Here,
Okay.
think of instead of trajectory, think of the wave function.
Okay.
Yeah. So it is like, I don't know if you've seen the movie Matrix. It's like very confusing. So whether you think in terms of particle, you can often get confused. So probably just think that, there is no particle, there's only the wave function. And then things become a little bit. So we can assign energy to the wave function. We can ask if the wave function has angular momentum, if the wave function has linear momentum. We can ask all these questions. And these wave functions are special because they have definite energy.
Okay. Thank you, sir.
Thanks. Yeah, that's a very good question, but unfortunately, yeah, it requires more quantum.
hello, sir.
Yeah.
I have a
Yeah.
question.
Yes.
Sir, the wave function, what type of function is that? Means, is it a complex value function?
Yeah, so you see the red guy, for example. So it's like a function in 3 dimensions. So it's like a spherical function in 3 dimensions. So, if you, just to give you one example. So have you studied Cartesian coordinate system, X, Y, Z?
Yeah.
Sorry, I don't know what class you are in. So yeah. So, and also what about the spherical coordinates? Have you studied spherical coordinates?
Yeah.
Yeah, so you take you take a function which is for example, say sine theta cosine phi.
Okay.
So that's one wave function that give you a wave function. So suppose you take, say, for example, r squared sine theta cosine phi. That's like a wave function.
All right, like that.
Yeah, like that.
And sir, is the position of the electron? Sorry, I mean the probability of finding electron with what distribution does this follow?
So that's the so this is the function. The wave function is say r square sine theta cosine phi. Now you square it, and that gives you, so r to the 4 whatever, sine square theta cosine square phi whatever. So that gives you the probability density of finding the particle as r theta phi. Finding the electron at r theta phi.
All right, so that gives us the probability.
Yeah, exactly.
Thank you, sir.
Probability density, yeah, and of course at a given instant of time. So it's like a snapshot. So these wave functions in general, of course, could depend on time. So when I say it's like r square sine theta cosine phi, means I'm describing at a given time.
Right, sir. All right.
Yeah, thanks. Okay, any
Sir,
other
does the wave
Yeah.
Sir, does the wave function have any other significance other than its square is the probability density?
Well, it has the it has the complete information about the electron. If you that's the most you can know about the electron. So it's like a mother of all objects in quantum mechanics. If you know wave function for a quantum system, you know the most you can know about that system. You can't know anything more. So using this wave function, you can not only compute probability, you can compute if you take a quantum system like electron in an atom and someone gave you the wave function, then you can ask, okay, what is the probability that the energy is 5 joules? What is the probability that the angular momentum is some in some units, some say 3 or 4 or something. So in quantum mechanics, about every physical quantity we can only talk in terms of probability, and probability of measuring any physical quantity and predicting its value is completely determined by the wave function. I don't know if that made sense.
Yes, sir, I understood.
So you see that as I told you that these are definite energy states. These wave functions have definite energy. So suppose you are in the S wave and someone asks you, what is the probability that energy of the electron in the S wave is, say, okay, just say some joules. Now, because it's a definite energy state, probability of measuring that energy is 100%, but any other energy is 0. So, the wave function already told you that if you measured energy of this electron, if it is in S wave, what is the possible outcome you will get of the energy?
Okay, sir.
Yeah.
Sir, what would be T0, for example, like if I just start observing an atom?
Yes.
Or for example, like the wave function has a position and a time, like parameters.
Exactly, yeah.
Yeah, so what would be our starting time? Because
well, that depends on how we prepare the atom, So if the atom, because atom, if it is in isolation, because T equal to 0 is your choice, right? So before.
Yeah, that's what I was thinking. So the electron doesn't depend on my choice. Like it's like qualities, right?
Right. But at T equal to -2 seconds, the atom could be colliding with some other atoms. So then, it could be in a different wave function at T equal to 0. But if you, just for hypothetically, for example, suppose you started at T equal to 0 in the S wave. okay, in the
Okay.
S wave, suppose. And then suppose the energy in the, as we are discussing, the energy in this wave is like definite energy, some joules, let's call it 1 joule. Then the time dependence is e to the I 1t. So this at future times, at t greater than 0. So it will always oscillate in time.
Yeah, so we need to first observe the atom to find out its like quality and then extrapolate from that.
No. Okay, so you're asking a very hard question. If you observe, because these are quantum systems, they are so fragile. If you observe, you disturb them.
But then how do we decide which state the electron was in before we plug it our waveform?
No. So when we say this, we are assuming that we prepare a system in some state. So you disturb it, exactly. So suppose you are given an atom, you don't know what state it is in, but you disturb it because you want to put it in S wave. So you disturb it enough so that it becomes it goes in S wave.
Okay.
And then you let it evolve. Is that okay?
Yeah, so it's just the disturbing part I was wondering about.
Yeah, thanks. Okay.
Sir, you said earlier in the talk that electrons follow have relativistic effects.
Yes.
Theory of relativity, and therefore its mass increases. What is the upper bound on the mass?
Well, upper bound, as we know, is infinite, right? I mean, so that's why we can never accelerate any particle to speed of light, because that requires.
So what is the speed of electrons? Is it not?
Yeah. So it will always be less than speed of light. Anything less than speed of light. You can go to any speed less than speed of light. You can never.
Order 10 to the power 8, they say.
Yeah, but you cannot, like, you can go to, if you assume speed of light is 3 into 10 to the 8, you can go up to 2.99999 to whatever nines you want, but you cannot reach 3.
So that is the speed of electron. Means.
Well, I mean, here, no. So in gold, the speed is determined by how many protons we have, right? Because 79 protons have like an electric force on the electron. And so that determines the speed of the electron. It's very high. It's very close to, it's like half the, I don't exactly remember the number, half the speed of light or something. So it's very, very high in the S wave. So they really feel the relativistic effect, these gold electrons.
Then it should means increase to infinite.
Sorry, why? Not infinite. Half the speed of.
Half the speed of light doesn't experience relativistic effects.
No, it does. So that's why the mass, exactly. That's why the mass increases. So that's the point, that mass keeps increasing, but the mass will, if you could accelerate a particle to speed of light, the mass is infinite. So that's why you can never accelerate any particle to speed of light. Any particle which has mass, you can never accelerate because that.
The mass will keep on increasing, right? And the speed will remain constant.
No, it's inertia, right? So the mass increase means it is resisting this increase, right? It is an inertia. So when we say mass increases means to accelerate it to certain velocity, we need to put more force. But if you want to accelerate to speed of light, you need infinite force. Remember, mass is the inertia. Mass tells you how much force you require.
All right. Thank you.
Good. Okay, so maybe I will move on if there are no other questions on this part.
Sorry, can it be ever possible that we can observe these fragile systems without disturbing them?
So the observation itself is disturbance in quantum mechanics. That's about, when you say that you observe, what do we mean, right? We probe it. We measure something about the system.
Yeah, throw photons at it, basically.
Right. Then we disturb it, because you throw photon, then you have as we are discussing, as we are seeing that some electrons will get excited. So, so the state of the atom will change.
Okay.
So the observation itself is, because when we observe a system, we observe a system using our tools that we have, which are like classical tools, basically. So they're large tools. So if you, intuitively, if you think that you want to observe an atom, no matter how carefully you want to observe, you end up always disturbing it a little bit.
Okay.
Yeah. Okay, so let me move on a little bit. Okay, so far we just saw that the sorry, Anudhan, by the way, let me know the time.
Yeah, sure. We start at 5:30, maybe like another, say, half an hour-ish.
Okay, no, just tell me when to stop. I mean, it's fine.
Yeah. Okay.
I'm happy to go on. I have no that way time limit. So whenever you guys are bored, you can just tell me.
Oh, no, it's really interesting. So yeah, I'm still curious about what is more to come. So.
Okay, so now, so we saw that we saw like a baby example of combining ideas of quantum mechanics and special theory, that we can, figure out fun and useless facts like why gold is yellow. But this is kind of just a beginning. So real fun starts when, you combine like two sort of, like what we can call maybe pop icons of special theory and quantum mechanics. So the icon of relativity, which everyone knows, is equal to mc square, of course. And the kind of famous icon of quantum mechanics is something called uncertainty principle. So uncertainty principle basically tells you that roughly tells you quantum system can never sit still. And the nicest way to understand is this joke that is kind of popular, that, there is Heisenberg is the physicist who formulated uncertainty principle. And so this is the joke that, he's driving on a highway and gets pulled over by a cop. And the cop says, do you know how fast you are going? And he replies, no, I don't, but I know exactly where I am. And, if he knew how fast he was going, then he would have no idea where he is. So that's what uncertainty principle is basically. If you know the position very precisely, then you don't know momentum, momentum less and less precisely, and vice versa. So that's the essence of uncertainty principle. And if you combine uncertainty principle and equal to mc square, you come up with a remarkable fact, which is very neat. That, suppose you start with a particle of mass m. And so suppose the energy is E. So let's say mc square, suppose it's at rest, it has no kinetic energy, then it's just mc square. And so let's say you take two particles, then, they will have energy twice the, at rest, then it will have energy 2e. Now, suppose these particles are quantum, and suppose you try to locate them, you try to find them, they are described by some wave function, and you want to find out the place where the probability is maximum. You try to find them by using some, detector or something. Now, uncertainty principle is telling us that if you locate them, then its momentum will become more and more uncertain. But if its momentum becomes more and more uncertain, then obviously its energy will also become more and more uncertain. So if we try to locate a particle with increasing precision in space, we cannot know if the energy is E or 2E or 10E or whatever. Or in other words, we cannot know that if in the process of finding one particle, we ended up actually producing two particles or three particles or four particles. And so this really happened because equal to mc square is there. I mean, so combining equal to mc square and quantum mechanics led us to this strange fact that, if you try to find one relativistic particle, you may end up messing the system so much you produce, two or any number of particles. And there is a small fun fact, which unfortunately we don't have that much time to go into. It is called Pauli exclusion principle, that although I call them twins, you end up producing twins. Actually, the two quantum particles can never be exactly the same. That is, if you measure all their properties, then there will be at least one property which will be different between them. So this, yeah. Okay. Anyway, but the main upshot is that, so this is what
laws are all empirical.
Say that again.
These laws are all empirical, means like Pauli's exclusion principle.
Yeah. Pauli's exclusion principle started as something, but it can be proved actually.
It can be proved.
Yeah, it can be proved. So it is the proof actually comes from what we will discuss in the remaining talk, this framework that we will discuss in the remaining part of the talk. Using that framework, we can actually prove it.
All right.
Yeah. So let me just switch to the next slide. So this is the price you pay if you really try to combine. So let me just recap. So we kind of got, okay, because we could explain some fun fact, we got excited. Let's try to merge the two theories, or at least some principles of these theories, like uncertainty principle and equal to mc square. And then we see that, we end up getting something which is very drastic, that we cannot work with definite number of particles. We have to allow to have any number of particles, because the moment we try to find these particles, we end up producing more particles. So combining relativity and quantum mechanics forces us to talk about not one or two or fixed number of particles, but arbitrary number of particles. But then, okay, then the question is, how do we do this? So to understand this, we go back to actually Maxwell. So I hope that some of you have, most of you have looked at Maxwell's equation, which describe electromagnetism. So if you have some question, please ask. I will assume that at least you have heard of Maxwell's equation in this slide. So from Maxwell's equation, you know that electric and magnetic effects are described by fields, like electric field and magnetic field. And these fields permeate the entire universe. So this E is the electric field, is a function of the space, which I denote by x, and time. So there is a field all around us, which is corresponding to the electric field, and similarly magnetic field, etc. And of course, Maxwell's equation are actually, they are compatible with special relativity. In fact, that was the whole crisis of how special relativity came, because Maxwell's equations were not compatible with the framework which was there before special relativity, which was known as Galilean principle of relativity. So we are kind of already in this relativistic world when we play with Maxwell's equation. Now, it was realized by Max Planck and Einstein, especially, that these electric and magnetic fields, their quantas are these particles called photons. So these electric and magnetic fields are fields, but if you look at them closely, they kind of lump together in these discrete wave packets quantum mechanically, and these discrete packets of energy, and these discrete packets are called photons. And if you increase the intensity of the electric and magnetic field, you start increasing the number of photons. So already from from early 20th century, we knew that what was a photon. Like it was basically like an excitation of an electromagnetic field. So now we can reverse the logic, because we want to understand how to describe a system which can have arbitrary number of particles. And for photon, we know how to do it. We work with fields. And we increase energy of the field, we can have any number of photons. So to describe relativistic quantum particles, what we can do is to use the idea of fields. So just like electric and magnetic fields are there, now we will assume that for every particle we see in nature, there is a field. And we just, for obvious reason, call it a quantum field. So this is the framework that is forced upon us if we try to combine the idea of special relativity and quantum mechanics, that that because the number of particles has to be arbitrary, the simplest framework to include that fact is to work not with particles themselves, but with these abstract objects which are fields, which are quantum mechanical fields. So by which we mean they obey uncertainty principle as well as laws of relativity, everything. And they are described like electromagnetic field, like functions of space and time. So this is like this is the start of a new paradigm that we end up developing if we combine these two principles. So a quantum field is essentially like, you can think of it like a ripple, which is permeating all of space-time. So for example, when we talk of an electron, like a relativistic electron moving with high speed, for example, then we, in physics, I mean, in this paradigm, we think of it as an excitation of a field. So there is a field, which is, let's just call it electron field, which is everywhere in space and everywhere in time. And it's these fields, when its excitations, when they have sufficient energy, then they basically behave like electrons that we see around us, like particles. But there are no particles, they're just excitations or quanta of this electron field. And this principle is true for any particle. So a particle X, whatever it is always an excitation of some quantum field. We just call it X field. So now it turns out that once this idea came about of how to merge special theory and quantum mechanics, then there was really no stopping. And this really kind of end up explaining everything that we understand about our world today. So by looking at all the quanta / particles that physicists were observing in experiments. So by this time, there were two things happening. Of course, theory was developing, and people were doing more and more sophisticated experiments, and like radioactivity, and so observing new particles. So basically, they divided this class of particles or fields into two types. One type of fields which are called matter fields, which describe all the matter we see around us, like electrons and as we will see this, there are other particles, matter particles called quarks and neutrinos, etc. that I will come to, but basically matter. So for now, maybe you can assume just electron. And of course, there are fields which describe forces between the matter particles. So for example, electromagnetic field, and the excitation of electromagnetic field is a photon field. So there are two types of fields we have: fields which describe matter and fields which describe forces between matter, like electromagnetic field. And this principle was actually, it has such a remarkable simplicity that there was a very simple framework which explained a lot based on this very simple idea. So let me just tell you the let me go a little bit forward. Is there a question? Sohan has a question, or no?
No, he was just answering one of the other questions in the chat. I think we're good to go.
Okay, cool. Thanks. Oh, is there a question in the chat also I should look at, Anirudh? Or,
oh, no. I'll voice it to you if there are any
okay.
answered ones.
Okay. So and actually, thanks to quantum field theory, I mean, yeah, I hope there are no chemists in the audience, but basically, in 18th century, chemistry was kind of star of the show, because periodic table was this massive zoo which seemed like very fundamental. Every metal, every liquid, every gas was contained in the periodic table. So it seemed like a structure which explained everything. But it turns out that it's just a giant mess, which is actually described by something much more simple and fundamental. So let's just see how physics superseded chemistry in that sense in the 20th century. So so here's something that we knew about atom before this merging of specialty and quantum mechanics, that we have an atom, and then there's a nucleus, and inside nucleus there are protons and neutrons, and outside there are electrons. But it turns out that now these protons and neutrons are not fundamental. I mean, they're themselves made up of even smaller objects, which are called quarks. So these quarks should be thought of as excitation of some field that we can call quark field. So that's our principle. So there are these various fields, electron fields, and then there are these other fields called quark fields. And these quarks are excitations which themselves combine to give you protons and neutrons. So already, one discovered something more fundamental than what we knew even about atom by combining these principles. So, so this is the sort of a slight mockery of chemistry in some sense. So 18th century periodic table was most fundamental, and because every known element could be understood. But quantum mechanics kind of taught us that this complicated table was actually, little too complicated. There's a universality behind it, which we understood as atoms. And this is something we understood already in early 20th century, that every object in periodic table is described by a fundamental quantity called atom. But now quantum field, this subject where we combine quantum mechanics and special theory, obviously it's called quantum field theory, because now we are saying that the basic object is a field as opposed to particles. And this quantum field theory explains even deeper structure underlying an atom. Like, for example, quarks, which come together to form protons and neutrons. And of course, then there are electrons, which we already knew from before in quantum mechanics. So now we have a new periodic table in some sense. But okay, before that, let me tell you something fun, that sometimes it's good to go back to, people used to just meditate in ancient times, like this Roman poet called Horace, who had this very famous line that we are nothing but shadows and dust. So QFT actually, quantum field theory, so I'm just going to call it QFT from now, it actually improves his poetry, that we and everything around us is nothing but quarks, electrons, and vacuum. That's it. So it's kind of, of course, when you do physics or mathematics also, you kind of meditate, but your meditation may be your more concrete ground in some sense. So just to sort of reiterate. So quarks, which are these tiny objects which make up protons and neutrons, they are quanta of quark field, and electrons are quanta of electron field. Photons, of course, we already knew from Einstein and Planck that they are these excitations of electromagnetic field. And in fact, it turns out that there were other particles that people were finding in 1930s for which there was no explanation. So in 1930, a physicist called Wolfgang Pauli had noticed that if you look at radioactive decay, so where radioactive materials like, I don't know, carbon-14 or one of these isotopes, when they decay, there is a problem. Like we know that in any physical process or any scientific process, energy and, for example, even angular momentum will be conserved. And Pauli noticed that in this radioactive decay, these things are only conserved if there was an extra neutral, that is electrically uncharged particle, with no electric charge produced. So he kind of termed this thing neutrino. Neutrino because it's neutral. It was not observed when he just guessed it, because some energy was getting lost and it was not clear where it was going. So he guessed that there has to be an extra particle which is carrying this energy in radioactive decay. And it was indeed observed in 1955 in an experiment. So now the question is that, we have all this zoo of particles and they are all going to be described by quantum fields. So is there a coherent framework which describes all this plethora of particles we start seeing together? So another interesting particle that I should just mention maybe is that, as I was saying, quarks are these particles which glue together to form protons and neutrons. But you can ask, like, what glues them together? Because something has to glue them. So for example, if you take a positively charged particle and negatively charged particle, then they are glued together by electromagnetic field or photons. And so these quarks get glued together by particles which are very, they're kind of like photons. They're more complicated to study, but they're, you can think intuitively like photons, and they are called gluons. Very unimaginative name, of course. And then you can ask, okay, what is causing radioactivity to happen? So I'm just listing the particles that people were seeing, and as you will see, they all get kind of explained by a very simple picture at the end of the day. So we have we had electrons, we have quarks, we have photons, we have gluons, we have neutrinos, and you can ask what causes radioactive decay. And this radioactive decay was suppose it is caused by some particle. Let's just call it W boson. For a reason it was called W boson, but some particles, which has excitations of some other field, which we just call W boson field. So we have like this plethora of particles which explain sort of physics around us, and the idea is how does we encompass all of this into a single framework. So this will be an improvement, massive improvement over periodic table, because it is going to explain every atom and fundamental structure in terms of these basic principles.
Excuse me, sir.
Yes.
Yeah, so how do the fields communicate? Because there is obviously communication since
very good
different
point.
Particles interact.
Yes, exactly.
Like different kinds of particles seem to interact.
Yes, exactly.
Yeah, so how are the fields communicating? Because an excitation in one field seems to be able to cause ripples in other fields.
Exactly. So the entire framework of quantum field theory is to explain how the fields communicate. So how do we write down rules? And I will come to these rules now. As you will see, they're very only you have to, you have only two basic pillars: special theory and quantum mechanics. So you want to make rules which are consistent with these guys, and with this guiding principle, can you write down rules which give you interaction between various fields? And it turns out that you can. I mean, that's the thing. So based on very fundamental principles, you want to write down rules that how these fields interact with each other. I don't know if that's what you are.
Yeah. No, I was just.
So for example, okay, just to give an example, that you can say that so we have an electron field and we have a photon field. And you can ask, how do electron field and a photon field interact? Because obviously we know they do interact. So, yes. Okay, so we have to write down some equation which is telling us that you have one function for the electron field, one function for the photon field. And how do we write an equation which tells us that these two are interacting with each other? So this principle of special theory and quantum mechanics actually tell you that there are unique ways to write these interactions. There is not much choice, so that you get the and that explains the observed phenomenon. So that's the remarkable part.
Okay.
Yeah.
Sir?
Yes.
Sir, in this standard model, there are three generations of matter. Are they are they caused by three different fields, or are they fluctuations in the same field?
No, very good point. So for our, it's a very good point. For us, they are all caused by different fields. So we are saying that we have you obviously know a lot more about standard models. So, okay, so maybe let's discuss this after this slide, because I was just coming to your, the thing you raised. So this is just give me 1 minute. After this slide, we will come back to your question. So this is the more fundamental periodic table, which is now the star of the show in sciences. So we can forget the chemistry periodic table now. This is much more interesting. So
this is a periodic table.
I mean, periodic table only in the sense that everything is explained in terms of these guys now. So that's everything except gravity, I must add. So I'll come back to gravity in the end. So if you forget gravity for a second, then all the things that we see around us are explained in terms of these basic particles or basic fields. So we have the names are not important. I mean, the names are initially people started using Greek names, taus and Mu1 and Tau and all, but I guess people ran out of Greek letters, so then just start calling it top, bottom, and this and that. But so basically, you have you have 6 quarks, so you can think them as having 6 quark fields whose excitations are the 6 quarks. Then you have this, you have electron, which we know, but this it turns out that similar to electron, there are particles which are very similar to electron. They have charge like electron, etc., but they are much heavier. And these are called muons and tau leptons. So these are particles which have same properties as electrons in some sense, but they are much, much heavier. And then this neutrino is what Wolfgang Pauli had postulated, which was found in 1955. But it turns out that theoretically, it was shown by physicists, these 3 physicists, that all these particles, especially these electrons and then neutrino, muon, some neutrino, etc., they fit together according to rules of quantum mechanics, but if and only if you have some other particles. So if you, for example, when they postulated this theory, I mean this framework is called standard model, by the way. So it's a particular model which explains all the matter and the forces except gravity that we see around us. And so they postulated that there is no way to combine quantum mechanics, special relativity together if we only had one neutrino. They sort of say that for the theory to be consistent, there had to be 2 neutrinos. So they called it Mu1 Neutrino and Tau neutrino. And indeed, these were found later in the experiments. Similarly, so there are these gluons which glue the quarks together. There are these photons which the electromagnetic carriers of electromagnetic force. The W boson is the force which carry out is responsible for radioactivity. And these 3 together would not make sense unless they predicted that there was another particle which they call Z boson. So this particle is again very similar to photon, but it had a mass. So it is a particle which has no electric charge like photon, but it has a mass. So it is a heavy particle. And indeed, this particle was found in later experiments, I think 10 or 15 years after they formulated this theory. So in that sense, this is a remarkable achievement also of standard model, that for it to be consistent, some particles had to be present, and indeed they are actually sort of present. Now, all of these particles, you can always ask one question. Okay, you have these particles. Some of them, for example, electron and I mean all the particles except photon and gluon have mass. So you can ask like, can quantum field theory tell us why some particles have mass and some particles don't have mass?
Photon doesn't have mass.
Photon doesn't have mass. I mean, mass is zero. But by that I mean mass is zero.
But I guess that
No
photon
mass.
has rest mass 0. While it is moving, we consider it to be mass.
Well, photon has no concept of rest mass, remember, because it moves with speed of light. Photon can never be at rest. You cannot go to any frame in which photon is at rest.
Any particle with mass can't reach speed of light, and anything with like no mass cannot slow down, or like it has to move at the speed of light, right?
Well, even if the particle which is moving with the speed of light is moving with speed of light in any frame of reference.
Yeah, I know. I'm just asking if any particle that doesn't have mass must move at the speed of light.
Yeah, exactly. Must move with speed of light. Exactly. Or you can reverse it also. If the particle is moving with speed of light, then it is necessarily massless.
Okay.
It has zero mass. Yeah, thanks. Yeah. So right. So but you can ask, okay, of course we know electron has some mass, and and these muons have mass, which have which they're very heavy. They have a lot of mass. Tau leptons. These tau leptons have a lot of mass. So what gives some of these particles masses, and what keeps some of these particles like photons massless? And it turns
Sir, I
out
have one question.
Yes.
Sir, what about the composition of atoms? Means if you consider any atom like that of gold or silver, anything. So are they comprising only of the electron, neutrino, or some other neutrinos?
No neutrino.
Also?
So any atom is comprising only of the quarks. In fact, only two quarks, up and down quark and electron. So remember, any atom has nucleus and electron. And nucleus has protons and neutrons. And it turns out that each proton and each neutron is composed only of the up quark and the down quark.
Okay, sir. So what about these Mu1 neutrino and Tau neutrino? Where are they found?
Very good. So yeah, so these are particles which are found in very high energy collision. So if you take like electrons and you collide them with some heavy atoms, etc., then these particles are produced. The reason these particles are very hard to see and we don't see them is because they're heavy. They're very short-lived, so they don't live long.
Yes, half-life. Yes.
Yeah. So
okay.
Yeah.
Sir, what about the speed of electron? Means we measure it to be something like 10 to the power minus 31 kgs, around that. So is that the means rest mass, or when considering relativity?
That's a rest mass. Yeah.
Okay, sir. But it's moving at the speed of light. So it must acquire some.
Electron is never moving with speed. Electron cannot.
No. Around the speed of light, I say. Sorry.
No. So you are asking about gold atom. So when we say that electron has a certain mass, or tau lepton or muon a certain mass, we always mean rest mass. Always. Okay. So if the particle is accelerated to high speed, we have to compute its mass, as you know, which will be by relativistic formula. So,
sir, but in under normal cases also, it must be moving at somewhere around the speed of light, means lower than that. So its mass should be more than that.
Yeah. So we know. Yeah. That's a very good point. So suppose I gave you some particle, it's moving with some speed, and then you could measure its mass, for example. But if you knew the speed of the particle, then you can compute what the rest mass will be, right? The mass.
Yes, sir. Yes.
Yeah, exactly.
Sir, whenever any element like this, like electron, is moving comparable to the speed of light, it increases some mass. So it should also acquire some kind of attraction property, like what gravity does.
Oh, that's a very good question. So I will come to gravity right in the end. But obviously, gravity affects every particle, whether it has a mass or not, because gravity affects anything which is energy. Right. So gravity affects gravity. Electron feels gravity, photon feels gravity, everything feels gravity. The point is that the gravitational force is very, very weak. And this is the only reason we can talk about these other forces, like, the force of photon, force of gluon, force of W boson, without talking about gravity, because inside the atom, gravitational force is very weak.
Okay. So, sir, the strongest force yet found is the force of gluons.
Exactly.
I guess.
Yeah. Thanks. Yeah. Okay. I didn't want to use the name, but you're right. That's called the strong force.
Sir.
Okay. Thank you.
I think
you
we'll
just
take a
said-
couple of questions towards the end. So let's see what's coming,
Oh,
waiting in the store.
yeah. What time is it? Oh, so
It's
we are way over
40.
time. Oh, I apologize. Yeah, maybe let me just go fast and I have only a few slides left now, I think. I'll finish.
So
Or
we'll
maybe
take questions towards the end, and
Yeah.
I'm sure there will still be questions. So write to us, and Professor Laddha will be extremely happy to answer them. So
yeah. But Anirudh, you can also cut me off anytime.
oh no. Let's wait until I want to see
Yeah,
the final.
I think I have only like few slides left. I'll finish.
Yes, sure. We'll take questions towards the end, please.
Okay.
Sorry.
Yeah. So we were talking about the mass, and also some people were asking. So the problem was that, okay, if really quantum field theory can explain all the properties of atoms and also particles, then how can it explain the existence of mass, existence of inertia? And this is, of course, it's a very deep problem, right? If you study Newtonian mechanics, mass is just something which is given. We can't even ask like what mass, where mass comes from. Why do some particles have? How do particles acquire mass? So this problem was solved by an absolutely remarkable proposal by a physicist called Peter Higgs, who is this guy. And so Peter Higgs has an idea, which is an incredible idea that I'll explain in the next slide, that he basically explained that if there was one more quantum field or one more quantum particle in the game, which this field we will obviously call the Higgs field because he is the one who proposed it, then its excitations, which are, they are called Higgs boson. That's not very important. Some Higgs particle, we can call them. They would create mass for other particles. And in fact, they would ensure that photon remains massless. So, and this idea, obviously this is a incredible theoretical accomplishment because on July 4, 2012, this Higgs particle was actually found, as many of you would know, in the Large Hadron Collider. So something that he postulated from theory in, I think early 60s or late 50s was actually confirmed as an experimental fact in more than 60 years later. And the idea is so simple that we can explain it using this fun advertisement, which is called the Higgs Party. So that I think there was some British MP who had challenged people whoever would come up with the most nice explanation of the Higgs field and Higgs particle would get some prize. And this is the poster by a physicist in Britain which won that prize, which is a very beautiful way to explain the idea. So here is the idea. So the idea is that suppose, so I will just read it out. Of course, it's written here, but I will read anyway. So suppose you have you have like a party of physicists, a party of people here, and so think of this this as a Higgs field. So this is like think of this physicist being like continuum, not discrete guys. So it's like a field, and let's not call it a Higgs field. And suppose like a newcomer, some star enters, and then because he's some like a famous guy like Einstein, all the other guys kind of cloud around him. So it's hard for him to move through the room. So he faces some inertia. So because of his popularity or his interaction with these other physicists, he develops an inertia, or he develops a mass. So this is basically the idea with which Higgs field gives mass to other particles, because it interacts with all the other particles in a way that they acquire mass. So that explains how particles get mass from Higgs field. So Higgs field you can think of Higgs field as like the master field which is permeating everywhere and interacts with all the other fields and gives them mass. And now you can ask, okay, what is a Higgs boson or what is a Higgs excitation? And that's not very hard to understand. So basically, suppose someone propagated some gossip, or maybe in today's time fake news, and so that fake news propagated through this room. So to hear that news, these physicists like clump around that news. So this clump is what will be like one excitation, which is called the Higgs particle. So this nice picture explains both what the Higgs particle is, what the Higgs field is, and also how the Higgs field may be able to give mass to other particles. And I mean, you may think it's a silly picture, but actually if you look at the equations in detail, they really kind of are quite fairly consistent with this very, very naive sound looking picture for the Higgs particle. So the Higgs field was necessary for the particles to have mass, and it was indeed the Higgs particle was found in 2012. So that's quite a remarkable accomplishment for this theory. Okay, now I'm going to tell you some small thing about gluons. It's almost my last slide. So gluons are the only other particles in standard model which are massless except photons. And just like as we saw, right, photons mediate electromagnetic force, gluons mediate before someone also said strong force, which binds these quarks together into protons and neutrons. But there is one difference. Photon is electrically neutral, and it can't, no matter what you do to a photon, how much energy you give it, it cannot produce other photons. because we know that photon, it cannot produce other photons because light is only produced when electrically charged particles are, heated or given energy. But photon has no electric charge, so it cannot produce light. So it cannot produce other photons. But gluon is more subtle. It carries a kind of a different kind of charge, which is usually called color. And it is such that it can produce its own copies, if you disturb it or give it more energy. So the easiest way to understand the comparison is you can think of photon as a solo instrument like this, and gluon is like a one-man band. The famous Goan artist who can play a lot of instruments, I think 32 instruments or something together. So he's like a gluon. Okay, now to summarize, I'm almost done. Maybe this is my last penultimate slide. So we have matter made out of quarks, electrons, muons, neutrinos, etc. And we have forces which are mediated by photons, gluons, and these, these W and G bosons. All the forces have different strengths and different properties. So just to give an example, W boson has mass and its force has a range which is really tiny. So that is why we don't see W boson or this force, which is usually called the weak force, in everyday life, because the range of the force is only within the atom. It does not farther outside. Opposite, of course, to electromagnetic force, which is present in everyday life, like in electric shock. If you want to experimentally verify electromagnetic force, of course you shouldn't try it. So you may think, okay, but so there is some, okay, we went deeper than periodic table, but it still looks like there are many particles and many forces. So is there some common theme behind all these particles and all these forces? They are really different. But it turns out that actually the power of quantum field theory is even deeper. And then there is a further universality, and this is what I will end with, that that if you go to very high energies or very short wavelengths, in quantum mechanics, because of the uncertainty principle, if you go to very high energies, that means you're going to very short wavelengths. All these particles and their interaction, as I think Sohan was asking, all the particles and the interactions with other particles start looking same. So this is a really remarkable fact. So for example, this is the two electron and positron colliding to produce a photon, or which I call gamma, or an electron and a neutrino colliding to produce this, it is called W boson, and or two quarks colliding to produce a gluon. But the structure of the equations that govern quantum field theory is such that they all have the same kind of math structure attached to them. So that they if you are at high energies or short distance, you can't distinguish. They all start looking the same. So there is a further abstract universality in this theory than even what we would have imagined. And this has an interesting offshoot, and the offshoot is the following: that if you say that, okay, if I take two particles and I collide and I see what forces mediate them, I know that I can have a photon, I can have a gluon, I can have a W boson, I can have a Z boson. Can I have anything else which is consistent with relativity and quantum mechanics? And it turns out, yes, there is something, and that's gravitational force. So the only other force you can have which is consistent with this picture and quantum mechanics special theory of relativity is gravity. So as you know, that there is this lore that Einstein created special theory, and then 10 years later he created general theory. But that's because he didn't know quantum field theory. If he knew, then just the principles of special theory and quantum mechanics or quantum field theory would have already told him that gravity is present in that. He would not have to do a separate general theory of relativity or something. So unification of special theory and quantum mechanics, in fact, leads to Einstein's theory of gravity. But that's really a subject for a different talk. So I will end here. And sorry for going over time.
Oh, thank you very much, Alok. This was it was extremely remarkable how you managed to glue the attention of pretty much everybody from grade 8 all the way to undergrads, with just a single topic of quantum mechanics. And yeah, the way you started from a fairly elementary level and went on to just building on it and got to great heights is incredibly amazing. Thank you very much for that. So I'm sure there will be plenty of questions based on the intuition you gave. So I'm afraid you might have to only type your questions in the chat. Please do not unmute yourselves. So I'll be reading out about 2 or 3 which we can answer now, and the rest of the questions we will get them answered a bit later.
Okay.
Yeah. So the first question. So is there a particular mathematical operation that determines how a particle is going to behave? That is, a particular behavior or a particular behavior or a wave behavior. If two operators defining a particle commute or something like that. Is there any operator like
that? So let me try to understand. So maybe I can read it, right? Maybe it's better to.
Yeah.
It should be in
early in the chat.
Oh, it should be in the chat. Okay. I don't know how to go to.
You can do Alt H.
Alt H. Alt H. Oops, but there should be a usually there is some window, right? That gives us the chat, shows us the chat.
Maybe stop sharing and then.
Okay, fine, cool.
Yeah.
And now I go to chat. Oh, cool. Okay.
Yeah.
And then you are reading the one from
This
bottom,
one,
or?
yeah, it is early, like somewhere very early into the session. Maybe I'll try copy pasting it. Maybe.
Yeah, better. Yeah.
I can find it now. I've scrolled all the way up. In the meantime, maybe just one more question which I have ready.
Yeah.
Is there any other element, or can there be one whose atomic number we can predict, which will deviate from the expected behavior, similar to how gold did?
That's an interesting question. I mean, I think that this is one question chemists will know a lot more. So obviously, when the periodic table was formed, I think the gold was in the last row of the original periodic table. But now, if you see periodic table, a lot more elements are there. So there are these non-natural occurring, metals and this mercury type liquids. I don't know, like I'm sure some of them have behavior which is like gold. They show different behavior than things around them. But I don't know any example except copper, which is red, and mercury, which behaves like liquid and doesn't behave like metal. I mean, as a solid. So I don't know if that answers.
Thank you. I've posted 2 questions on the chat.
De Broglie's, that one, De Broglie's formula, that one.
Yeah. That was one.
Yeah, okay. That all matter has wave nature. Okay. Without giving any particular reason, is there a way to explain wave nature of matter, not relying on observations from any experiment? This is an excellent question. So I think, I mean, the history of quantum mechanics is a little bit interesting in the sense that it did not develop as a mathematically sophisticated theory. So you are absolutely correct that the way de Broglie kind of gave his proposal was really based on some empirical evidence and how he could like fit different experimental data and Bohr's theory of atoms. So he combined things together with some very strong physical intuition. So at that point, there was no real mathematically rigorous theory which told you that why particle has to behave like a wave. And the wave nature of the particle is a postulate of quantum mechanics. So this is important to understand. So we do not we do not have a, as far as I understand, we do not have a deeper theory which tells us why the world is quantum. I mean, your question really is that, why the world is quantum. And as far as I know, there is no theory which can tell you why the world is quantum. I mean, every theory that we are trying to now that we are developing, which explains everything from very small scale objects to very large scale, assumes quantum mechanics, assumes postulate of quantum mechanics. So at its base, it assumes that the quantum particle is described by a wave function, and we don't have a deeper theory which tells us why that is so. If that, I think that was your question. I mean, it's an excellent question, but I don't think there's an answer so far to that. I hope that helped.
That was great. Thank you.
And then if we apply the, is that one? If we apply.
Okay, maybe like a smaller one. Why exactly do some particles interact with the Higgs field more than the others?
That's a very good question. So it's not more or less really. It's the so standard model basically is a model. So the idea is that we have a framework of quantum field theory, which is like a merging of quantum mechanics and special theory. And we had like the zoo of particles, and then we wanted to see whether quantum field theory can explain these particles. So people came up with a model, and that model is such that it explains all the particles that we see today in nature, which is remarkable. But it's a model that it's important to understand. So it's not like a fundamental theory in itself. So so in that sense, Higgs field is something that gives mass to some particles we know that who should have masses. I don't know if I'm able to explain it properly. So we have sort of there is some input in the equations that we are writing down, which ensure that he give mass to some particles and not to the other particles. But what is important is that this is not trivial. So it is not obvious that we will be able to do it in a consistent way. The fact that we can do it in a consistent way, consistent with the theory of relativity and quantum mechanics, is non-trivial. But of course, we are using the fact that photon doesn't have a mass and electron has a mass. And the idea is there a phenomena which can fit into both. That's what we are trying to do. So is there a fundamental theory which can explain standard model? That's an open question. that we hope that there's a theory called string theory, which will explain standard model from more fundamental principle. But right now, in some sense, it's an open question whether there's a theory which tells us why our world is described by standard model. So this question has the same flavor as the previous question in some sense. Why standard model explains our world, and I think that only string theory eventually will be able to answer that question. Okay, I don't know if that's
that I think was a good answer.
Soham is it? Okay. And then the next one, is it the long one?
Yeah, okay, we could take that.
Yeah. Or is there any? Okay. If we apply the so quantum mechanics doesn't tell you that if you have two particles, particle A, particle B, then you cannot, if you measure position of one, then you cannot measure the momentum of the other. The uncertainty principle is for a single particle. So the idea is that if you have proton and if you measure its momentum with precision, then you don't know where it is located. But it will not tell you that. That means you cannot tell where the neutron is located. I don't know if that answered the question that he asked. Is that what it will be? If they can unmute and ask, maybe it's better.
Yeah, okay, sure. Maybe like 5-10 minutes, maybe.
Okay. Yeah, maximum, right? So we are out of time, is it?
Oh, no, we are good on time. It's okay. Like 5-10 minutes, we can go.
Okay. 7 is the cutoff usually, right? Yeah.
Sir,
yeah.
Sir, I have a question. Sir, how much light is exactly a photon or a quanta of light, like quantitatively, and how can we estimate the value of Planck's constant using it?
Okay, that's a very good question. So Planck's constant was estimated, remember, using I don't know, sorry, I don't know what class you are in, but the Planck's constant.
Sir, I'm in 10th standard currently.
10th standard, okay. So basically, like, everything started in some sense in quantum mechanics from Planck's constant. So you may have heard that there was a paradox in physics that this black body radiation that you could, you take a black body, you heat it, and then you look at what light it is emitting, and the classical physics could not explain the observed light that it was emitting. And Planck is the one who proposed that the emitted light was coming in discrete packets, which were given by some constant times the frequency of light. So he looked at that data, which the light was emitted, and then he said that, okay, for a frequency of light, which is say some hertz, the quanta is some number times that hertz, and then he computed that number, and that is a Planck constant. That's how Planck's constant was computed. Is that I don't know if that answer your question. So
yes, sir. That means it's from experimental.
Exactly. You are asking how we can theoretically compute it.
Yes, sir.
Oh, no, we don't know. Yeah, I mean, so these are called fundamental constants. So, we don't have a theoretical understanding of why Planck's constant is something so far.
Okay, sir.
Like speed of light, we don't, ultimately when there's a theory which explains everything, we'll be able to tell us why Planck's constant is some number. But right now we do not have that. So these numbers, the Newton's constant, speed of light, and Planck's constants are like fundamental. That's why they are called fundamental constant, because they are not derived from any theory. But it is one number. It don't change with different phenomena.
Thank you, sir.
Thanks. Okay.
There's one more question from Arnab Chauhan. How do we measure the mass of quarks, because they cannot be isolated?
Oh, that's an excellent question. So yes, it is true that they cannot be isolated. But basically the point is that you have to take, for example, this is a bit of a hard question to answer. I mean, the one way to understand this is that you can take, for example, a proton, because you can isolate, say, like take a nucleus, and then you can take nucleus and make it participate in various reactions. So, for example, a very high energy reaction, such that the neutron will, the nucleus will break into protons and neutrons. And then by looking at these different reactions, you can compute what the total energy of the outgoing particles are. And if you have enough data, then you can use it to compute the mass of what constitutes proton and a neutron. I mean, I should say that, okay, this is actually a hard question. I'm not doing a very good job. So I should say that if you take a proton, and if it so a proton is composed of 2 up quarks and 1 down quark, and a neutron is opposite. It is composed of 1 up quark and 2 down quark. But the total mass of the proton is much larger than masses of the quarks, because most of the mass is coming from gluons. So the idea is that you have to really study a lot of processes to isolate mass of quarks and gluons. I mean, it's like, yeah, it's maybe the one thing I can do is like maybe set some links where these things are, some popular articles where these things are nicely explained. Yeah.
That would be great. And maybe like one final question. After this, we should come to a conclusion.
Yeah.
So is there an indication that the particles in the standard model are in fact fundamental?
No, I don't think so. I mean, what is amazing and at the same time a little bit maybe frustrating is that standard model was, as we are discussing, it was a model based on fundamental principles of quantum field theory to explain the zoo of particles. So people would have hoped that as you go to higher and higher energies, you may find new particles which are not part of the standard model. So the standard model was formulated in 60s. And of course, after that, there have been so many experiments in particle physics. And now we have Large Hadron Collider, which is going to astonishing energies. But so far, we are not finding particles which are not part of standard model. So, but that does not mean for sure that, there are no other particles. I think, in fact, it is theoretically, it is almost impossible. I think that we are fairly sure that if you go to very high energies, we will see new particles which are not part of standard model. Yeah, I mean, it's just a question of how high we can go with energy and when. So we need like new colliders which can go to even higher energies. But because nothing is telling us that standard model is fundamental as a theory. It is just something that is designed. It is part of maybe a fundamental theory like string theory, which definitely has more particles. So yeah, I would think no, although we have not found any. But I will just add one more thing, that there are phenomena which we are not able to explain using standard model. And this is called, in fact, majority of matter in our universe is, we don't know what it is comprised of. It's called dark matter, dark because we don't know what it is. And, it could be that dark matter is, composed of something which is not part of the standard model. We don't know yet. So, yeah. But yeah, I would not think so. Standard model would not be end of story, that's for sure.
Okay, thank you very much. I think okay, so so for the rest of the questions, I think all of you have my WhatsApp number or Amik's WhatsApp number, or you always have our email ID. So do send it out to us, and we'll get it answered as soon as we can. We're running a bit short on time, and so please do join me in thanking Professor Alok for this wonderful lecture he has given. So
no, thank you for listening
very much
on Sunday. Yeah.
Thank you very much. So we next meet at 10 p.m. today when Professor Ravi Vakil of Stanford University will be delivering a talk titled From Doodling to Mathematics, where it's a suspense for all of us. So thank you very much. Thank you, Professor Alok, once again.
Thanks for
accepting our invitation.
Okay, no, thanks for calling me. Yeah. Thanks a lot. Bye.
Thank you, sir. Bye.